Just before we talk about partial fractions, I want to have a quick look at the syllabus and show you what we're trying to avoid. What we're trying to avoid is integration by parts. Actually, you might end up enjoying integration by parts. I quite enjoy integrating by parts. But it's not always simple and it's not always obvious how to do it. And it usually takes a bit longer. So we're using a few techniques here, in particular integration by substitution and using partial fractions where necessary, because they can help us to avoid integration by parts. Now, be careful. The syllabus says use partial fractions where necessary for integration in simple cases. Your textbook does go beyond simple cases, and I'm going to highlight that again for you later when we get there. Okay, partial fractions. Sometimes you want to integrate something that looks like this. It's got a complex denominator that involves multiple factors. How on earth am I going to integrate that? Well, if I could separate this fraction into something over x plus 2 and something over x minus 5, then I could integrate the two pieces separately and each piece would be pretty easy to integrate. But how on earth do I turn this into that? In particular, how do I work out what I have to put on top of these fractions? Well, that's the magic of partial fractions. So, the general statement says, if none of these have any common factors, that basically means take out any common factors at the start before you go any further. If there's no common factors between these, then it's possible to come up with A and B, non-zero, so that these two fractions add to this, and then you can integrate this instead. If it's a single thing squared, then you look for a single version and a squared version. And there's some more complex cases, which we'll have a look at the end. And again, I think most of them go beyond the simple of the syllabus. But how do I figure out those numbers? Well, first, a theoretical approach. So let's have a quick look, a theoretical look, at how to solve this one, the one we started with. Suppose I want to write it as a over x plus 2 plus b over x minus 5. Well, this is a fraction sum. If I want to get the same common denominator, I would go a times x minus 5 plus b times x plus 2. And that's exactly what we've done here. Now, if I expand out the numerator, because the denominators are the same, if I expand out the numerator, I get ax plus bx, and I get negative 5a plus 2b. This together has to equal 0x plus 28, the thing I started with, on the numerator on the other side. Now, of course, it is possible to get out of these two equations. 0 has to equal a plus b, and 28 has to equal 2b minus 5a. There's two equations. You can solve those simultaneously. You get two numbers and you put them in. That's all well and good, but in practice it's actually easier to solve it a different way. You are effectively doing the same thing, but the method you go about solving the equations is a little bit different because it's a bit easier. Have a look at the next few videos to see how that's done.